Okay, can people hear me? Okay, can we get the slides up is the next question. Perfect. Oh, there we go, cool. All right, so convolutional models. Can I get a show of hands in here? How many people have used a convnet before? Okay, and how many people here know what a ResNet is? Okay, cool. So I think there should be something for everyone. Those of you who are more experienced will hopefully, get some little insights, and those of you who are less experienced with convnets should hopefully, by the end of this, know how convnets work. And those of you in between will hopefully, maybe get a little bit new intuition or something like that. Start my timer. So, I hope there's something for everyone here. I also hope that you'll get a little bit of a taste of the sort of state-of-the-art techniques in convnets. And in particular, I hope by the end of this talk that anyone here would be able to come up with their own convnet architecture and sort of be able to think about their data or their application and make choices about how they want to design their network. And I also want to highlight some of the sort of best practices that we see in convnets. So, should you use a 3x3 convolution? Should you use a 5x5 convolution? Questions like that. I hope by the end of this talk you'll have some idea about the answers to, at least. And some questions. Having more questions is never a bad thing. So, let's start at sort of the beginning of convnets, which is Linnet. So Linnet was sort of the first convnet that saw, I guess, widespread success. And this was on classifying little pictures of images from postal codes, the MNIST data set. And as you can see here, Linnet is it's a pretty simple. Can you guys see this laser pointer at all? No, okay. So, I mean, as you can see here, I've got a little diagram, and you can see that Linnet's not all that complicated. And basically, all it added to the sort of neural network world at the time was convolutions and pooling. And in particular, it used 5x5 convolutions and average pooling. Yet, with these two small changes from a sort of standard neural network, it's revolutionized computer vision. Maybe people didn't know it yet, but here we are 11 years later, and we're still using convolutions and we're still using pooling. So what was so special about this network? Well, the first thing was the convolution operation. So let me give you a little description of how convolution works, and then maybe go into a little bit of a description of why it's so useful. So if we have an image, this is a very simplified, idealized image, but it's just a bunch of ones and zeros in a 2D plane. So there's no channels, it's a black and white image, let's say. And we've got this little pattern here. I don't know how well you can see it, but we've got a little cross pattern here in light blue. And we want to find a pattern. And in particular, the pattern we want to find is a sort of downward-facing diagonal line. We can then use a convolution operation to sort of highlight that pattern within our original image. So if we apply the convolution, we apply this filter, we convolve this filter here with this image, we get a new image out that looks something like this. And hopefully you can see that our sort of downward slanting diagonal is now, it's been highlighted. It's a little bit brighter, the numbers are a bit bigger on that downward diagonal. But how exactly does this work? So what is actually happening is we take our little filter, which describes the pattern we're trying to bring out of our image, and we place it on top of our image, and we say, okay, what's 1 times 0? 0. What's 0 times 0? 0, etc. for all of the 9 pixels in that grid overlaid on top of that grid. And we get the answer out, which is 2 in this case, and we put a 2 over there. And we take our little grid of pixels, our pattern, and we slide it all over our image up and down until we've covered every pixel. So, we might move it here. We'll take this little grid here, multiply it element-wise with this grid, add everything up, and we get a 0 over there. And then we can do that again. So we put our grid over here, multiply everything element-wise, add everything up, and we get a 1 over there. And we do that for every single possible patch we can. So one thing that you might have noticed is that this little grid over here, there's an edge, there's a boundary as to how far it can go across our image. So what we often do in that case is we pad our image with zeros around the edge. I hope you can see that these sort of zeros are grayed out, to indicate that that's our padding values. So the idea there is that our original image was actually only this little square over here, but we added a little bit of padding around the edges so that our final image was a bit bigger, but more importantly, so that our filter over here would be able to sort of line up with more parts of our image. So that's what a convolution does. And of course, we could do it with any pattern. It doesn't just have to be a downward-facing diagonal. It can also go upwards, and in that case, we'll highlight a different part of the image. So I guess, does anyone have any questions about the sort of convolution operation that I've shown you here, or is this pretty clear? Okay, and feel free to stop me at any point with questions. We have got a mic that can get sent around, so if there are any questions, please do ask them. But okay, let's move on. So that's what a convolution operation does. But what does the actual convolution layer do? So a convolution layer is you can think of it as a function which takes in our image, and it returns a new image. And that new image is actually more like a set of images where we've highlighted a bunch of patterns in our original image. So in this case, I'm showing 2 highlighted patterns, and that corresponds to the 2 filters in this convolution layer. But you can have as many filters as you'd like. We're not restricted to only having 2 filters. So I guess the next question is, okay, why do we care? Why do we want to highlight little bits of images? And the answer to that is, in traditional computer vision, machine learning for computer vision, what's typically happened is that people have looked at images and said, wow, this is really hard for a computer to understand. It's just a bunch of ones and zeros in like a 2-dimensional or 3-dimensional grid. Like, how can we come up with algorithms that do anything with this data? And the solution there has been to use patterns, much like these little ones here, like upward-facing slants, downward-facing slants, crosses, circles, things like that, and slide them over our images and see how much of those little shapes we see, and then treat that as a feature that we feed into a neural network or something like that. And typically, in the past, that was done as 2 steps. We would manually apply these convolutions and filters to an image, take our resulting highlighted images, flatten them out, treat them as like an array of values, and feed that into some sort of machine learning classifier. But now, with a convolution operation, what we can actually do is figure out what patterns are useful automatically. So now a person doesn't have to sit and think, I wonder if an upward slanting line is a useful pattern for my use case. We don't have to worry about that anymore, because now that we have this layer with some weights, we can use backpropagation and just learn which filters are useful. So, and what's really interesting is that you can stack these convolutions on top of each other. So what that means is we can get sort of hierarchical features. So the things we highlight in an image become new images that we feed into the second layer of convolutions, and we can highlight things in those highlighted images and sort of build up these representations. And you can see this in practice. So there's a really cool paper by Lee et al. From 2009 where they sort of visualize features at different levels in a convolutional neural network. So this is what the first layer looks like. You can see the sort of downward slanting lines like we had before, a sort of weird black circle, some horizontal lines, and they all look very simple and uninteresting. But the magic sort of happens when we look at the second layer of the convolutional neural network. And now, so on the top I've got the original first layer features, and on the bottom there I've got sort of the features, the filters that we've learned in our second layer of our second convolutional layer. And what you can see now is they're much more interesting, first of all. We've got little guys over here, we've sort of got little circles, maybe like a slight angle over there, and they're starting to become more interesting. You can imagine, piecing a whole bunch of those together to get more interesting things. And in fact, that's what does happen. So in our third layer, we start seeing things like this. Now, this convnet that we're visualizing here, the third layer of our convnet, was trained for classifying faces. So what we see is we start seeing things like noses and eyes and mouths and all sorts of stuff like that popping up. And then we can even go a step further, and in our fourth layer, we start seeing things like this, whole faces. And this is this like incredibly powerful magical property of not just convnets, but sort of neural networks in general, which is that as you stack up more and more layers, you start to get these really interesting features popping out. And in particular with convnets, we get these sort of really cool to visualize pictures of faces, and if you train this neural network on cars, you'd start seeing cars and wheels and tires in the third layer. If you trained it on sort of animals, you'd start seeing like wings maybe, or tails and things like that. And so you can sort of start to understand now why convnets are so powerful. It's like they take things that start off looking totally incomprehensible, just these ones and zeros, and they sort of, in this hierarchy, build up a sort of understanding of what's important for our task. So, okay, we've spoken a little bit about convolutions now. Are there any questions about convolutions? Is everyone sold on why they're cool, how they work, things like that? Okay, so let's move on to sort of the other contribution, which was the pooling layer. So what a pooling layer just does is we can also think of it like a function, and it's a function that takes in, again, like an image, an array of numbers, either in a 2D or a 3D grid, and it says, okay, I'm going to do some aggregation on those images, on that image to make it smaller. And the specific type of aggregation is sort of up to you. In this case, Lynette used an average pooling. So what that meant was that every 4 pixels, they would just say, what's the average of those pixels? So the average of these 4 over here is 4 over there. And then we'd slide our sort of 2x2 window across and say, what's the average of these 4 pixels over here? It's 2, and again, it's very similar to the convolution where you sort of slide a window all over your image and you get something out. And okay, you can maybe it's more clear why a convolution layer is useful, but why would we want to make our image smaller? Well, there's a number of reasons. First of all, the smaller our image gets, the sort of faster we can process it, which is quite useful when you're training a really deep neural network. Sort of training speeds can be quite important. There's issues of invariance, which I'll get back to a little bit later. And then there's something called parameter reduction. So again, if our image is smaller and we flatten it to put into a fully connected layer, that will use less parameters than if we had a big image. And again, that could make things faster. It also saves us memory, for example. But one of the really interesting things about convnets, and sort of where pooling does come in a little bit, is this idea of receptive fields. Before I get to receptive fields, and actually, I suppose I skipped over a little bit of this. So with a convnet, so here, for example, I mentioned already that we can choose the number of filters we want to learn, and in this example, we've got 2 filters. There are a whole bunch of other parameters we can sort of control for, which are our hyperparameters, like the stride of our convolution. In other words, when we taking this grid of our filter, like how far across do we move it each time, how much padding we add. You can do all sorts of interesting things where you take your filter and you actually like spread it out a little bit and fill in some zeros. That's called dilations. There's all sorts of options for, the hyperparameters of our convolutional neural network, which we'd like to consider in various cases. The same is true of a pooling layer. So the first pooling layer over here, we had a stride of 1, which is to say that we took our 2x2 grid and moved it across by 1 each time, and then down by 1, and across by 1, and across by 1. But we could have done a different stride. Whoops. So in this picture over here, I've illustrated what a stride of 2 would look like. So in that case, we did our 2x2 pooling over 4 pixels, and then we jumped over to a whole bunch of new pixels that we haven't seen before. And you can really see now, with a stride of 2, how much smaller our image gets. And that's, again, something we can control, how fast we want to make our image get smaller, for example. So yeah, let me talk about receptive fields. So this is a sort of idea of we've got our input image over here, and we've got our output image over there. Now, this pixel over here, this 4 in our output image, we calculated that the value of 4 came from these 9 pixels by adding them up and averaging them. That's how we got that 4 there. So what that means is that the value of 4 in our output image depends on 9 pixels in our input image. Now, what we really want is for, at the end of our convolutional neural network, we want our final result to depend on everything that was in our original image. We don't want it to only depend on a small patch of the image or 9 pixels in the image. It must depend on that whole image. So what we could do is say, okay, let's use a bigger convolution. So in this case, we've done the same thing. We've taken a convolution of those pixels over there, and we've gotten a value of 4. However, this time we've used a 4x4 filter. And so our output pixel depends on 4 of the input pixels. Now, the problem with just doing this and saying, let's make our convolutions bigger, was twofold. First of all, it's not really scalable. If we want a pixel to depend on many pixels, we can't just keep making our filters bigger and bigger and bigger. And the reason we can't do that is because it's going to, A, be slower and slower and slower to do that convolution operation, and B, we're going to use more and more and more parameters. So that's not really a good approach. So what can we do? We can stack convolutions. So here, we've got 2 convolutions, a 3x3 convolution that takes this image over here and gets us sort of our intermediate image over there, and then another 3x3 that gives us a final pixel over there. So now our final pixel there, the 9, depends on every value in our input image. So that's cool. And of course, again, we run into a similar problem of, if our input image gets bigger, then we have to add more convolutions. So that is an issue. But what's nice is that doing sort of 2 3x3 convolutions like this is actually, well, it uses less parameters than a 5x5 convolution. In this case, because we're ignoring the issue of biases, well, we have been so far, that's 9 plus 9 is 18 parameters, whereas a 5x5 filter would be 25 parameters. So that's better. It's also much faster. If you do 2 3x3 convolutions, it's about 3 times faster than if you did a 5x5 convolution. So this is sort of a much more scalable approach. But there is a potentially even more scalable approach, which is to do convolution followed by pooling. So now we've done a sort of similar thing where we've got a 3x3 convolution that takes our input image and gives us a sort of intermediate representation image. And then we've got a 2x2 pooling that gives us our final image. So this might not look like as good a solution because now our 9 over here, okay, it depends on 4 pixels over here as opposed to 9, and then on 16 pixels here as opposed to 25. So we're not covering as much space, but we've sort of done this for free. We haven't used any extra parameters. We're only using our 9 parameters in our original convolution layer. So this is sort of like, this is why Linnet used pooling. It was to, reduce the number of parameters in the net needed to have a sort of big receptive field. Well, it's one of the reasons. As I mentioned, there's others. But that's a sort of important point. Okay, so are there any questions about pooling so far, or about convolutions, or about anything? Okay. In that case, let's move on to AlexNet. So I said Linnet was sort of the starting point for convolutional neural networks. It was the first one. It was where everything started, and it's what we have to thank for, all the ConNets we see today. But that almost wasn't the case. And the reason was that Linnet, the approach they were using was only successful for these tiny little images of postcode numbers. So these are like 32 by 32 black and white images. whenever people tried to apply the same idea of convolutional neural networks to other domains where we've got sort of maybe 200 by 200 color images of thousands of classes as opposed to just, the 10 digits, we ran into issues. And so people sort of didn't really think that the approach scaled, and there wasn't a lot of enthusiasm about it. That is until 2012, when Alex Krzyzewski and his co-authors won the ImageNet competition using a convolutional neural network. So what is ImageNet? For those of you who don't know, it's a competition where you get given images, 224 by 224 pixel square images, color images of thousands and thousands of classes. And you have to train some sort of classifier to automatically classify those images. And before 2012, the approaches that always won the competition were what I mentioned earlier, where people would sort of manually come up with convolutional filters to use as feature extractors, apply those feature extractors, and then take those features and feed them into some sort of machine learning algorithm, maybe a neural network, maybe something else. But in 2012, AlexNet came along and blew all the competition out the water by a very large margin. And that's really when not only the sort of convolutional neural networks started taking off, but the whole of deep learning. It was really a wake-up call for a lot of researchers to say, hold on, these approaches, really do work, and they scale, and they can beat sort of, handcrafted features. So, okay, what is AlexNet? And why did it work where LeNet didn't? So I think probably the biggest change from AlexNet to LeNet was actually just the amount of compute power available. The sort of like the crazy thing that Alex Krzyzewski did, which is why it's called AlexNet, is he decided he was going to train this ConvNet on GPUs. And this was something that had been tried before, but I'm actually not sure why it didn't work, but Alex did something right. He had the magic sauce. And so they took this idea of having a really big, powerful convolutional neural network with lots of parameters that was very slow to train, and threw hundreds and thousands of examples at it and spent tons and tons of time training it. But because they had this GPU that was somewhat feasible to do, well, actually 2 GPUs, and yeah, they had this amazing success. A few other things they did, they used something called grouped convolutions, and that's sort of indicated in this diagram here by the sort of separate blocks. So basically what's happening in this diagram is we've got our sort of input image, a 224 by 224 by 3 image, and we apply a convolution, an 11 by 11 convolution. So that's also another change. They're using a bigger convolution there. LeNet just used 5 by 5. They've now got an 11 by 11 here, a 5 by 5 there, a 3 by 3 there. So they're doing all sorts of things. With a big stride, they get a sort of new image out. They apply some max pooling, do some more convolution, more pooling, convolution, pooling, convolution, pooling, convolution, and then they flatten everything and feed it into a sort of standard feed-forward neural network. It's a big feed-forward neural network. It's a 2,048 hidden units there, 2,048 hidden units there, and 1,000 output units over there. So lots of parameters, very computationally intensive. But yes, they use these grouped convolutions. So what is a grouped convolution? Well, a typical convolution can be applied to an input image with any number of filters. So in the examples I was showing you before, we only had, not filters, channels. We only had one channel. I said, let's pretend this is a black and white image. But how do you apply a convolution to a color image? You've got you can imagine it as 3 distinct black and white images that we have to somehow combine in our representation. So the answer is actually, it's really simple. All you do is you pretend that sort of 9 by 9 grid now, because remember before we had a 3 by 3 grid, now there's a sort of extra dimension. You just treat it as though it was, as though it was flattened. There's no big difference there. There's basically nothing different to do. So what this means is that a convolutional neural network or a convolutional layer in a neural network can take in some arbitrary number of channels of an image. So it could be a black and white image, a color image, or sort of, a many-channel image with maybe 10 channels or, 100 channels in theory and in practice. And it can then output another arbitrary number of channels, and we can always choose how many channels we have. But what a grouped convolution is it says, let's make some of our filters only work on some of the input channels. So maybe our image has 4 input channels, and our convolution has 4 filters. Let's say 2 of those filters should only work on the first 2 channels, and the other 2 filters should work on the other 2 channels. And that's sort of why there's 2 blocks for each convolution layer. It's that this convolution over here only works on sort of the output of these bottom filters, and this higher convolution over here only works on the output of these filters. And the reason they did that was so that they could split their stuff over 2 GPUs. They had all the stuff on the bottom running on one GPU and all the stuff on the top running on the other GPU. And every now and then, they would send things between the 2 GPUs to sync up. And that actually has a really cool side effect, which is that the filters learned by our sort of grouped convolutions on one GPU and on the other GPU are sort of adapted to do different things. So here, these first 3 rows are filters learned by the top row of the sort of top GPU, and the bottom 3 rows are filters learned by the bottom GPU. And what's really cool here is that you can see that the top filters are largely independent of color. It's all sorts of things like, are there lines going up, down, horizontal, stuff like that. And the bottom ones have learned things like, is there a gradient? Is there a patch that goes from pink to green? Or is there sort of starburst for a pattern where there's blue in the middle and it goes out to yellow? And what was interesting is that this happened every time they trained the net from scratch with random initializations. One GPU would always, the filters on one GPU would always specialize for black and white and sort of patterns, and the filters on the other GPU would always specialize for color. So I thought that was pretty cool. Doesn't really have much to do with the rest of the talk. I just thought I'd throw it in there. Okay, so what else did AlexNet do different other than just put things on a GPU and train for longer with a bigger neural network? They also used max pooling instead of average pooling. So it's a pretty similar operation, but instead of taking the average of the square now, we take the maximum. It might seem like a totally sort of arbitrary change, and like, you might think, why would you do that? Like, doesn't that mess with the backpropagation? But in fact, this has a very nice property, which is that when you use max pooling, you actually increase something called the translational invariance of a convolutional neural network. So that's the idea that maybe you've got a face detector. You don't actually care if the face is in the top left-hand corner of your image or smack bang in the middle of the image or maybe the bottom right-hand corner. That shouldn't matter to your classifier, and it shouldn't matter to the convolutional neural network at all. And convolutions have this property because we're taking these small filters and sliding them all over our image. Those small filters, it doesn't matter if it's in the top left corner or the bottom right corner, it's still doing the same thing. But by using pooling, you can actually increase this property or improve this property, because now it's saying, okay, in our original image, let's say the 9 here was some feature we really cared about. Maybe it's a nose. It's saying there's a nose in this top left corner. But again, we don't really care that the nose is in the top left corner. We just care that it's there. So now it's saying, okay, well, the nose is in this top left corner, but it's a sort of shrunk space. All we care about is there is a nose somewhere there. It doesn't matter exactly where. They also use something called the ReLU activation, which probably all of you know what it is. But in case you don't, the idea is that we just take all the negative numbers in our array and make them zeros. And again, it's like a super simple change. Like, why should this make such a difference? But the reason it makes such a difference is that it actually allows us to train deeper networks. Okay, why do we care about training deeper networks? Well, the deeper our networks are, the more sort of interesting and complex features we can learn, in the sort of hierarchy of features. And the better our the larger our receptive fields are at the end of our net, and sort of the more non-linearity we can throw in there, and there's all sorts of reasons we want our neural networks to be deeper. There's more parameters, but less overfitting. You know, if you could just add parameters as many as you want in any layer, but if we sort of go wide rather than deep, we're more susceptible to overfitting. So deep is generally a good idea. I think we're all at the deep Indaba. We know that deep's a good idea. But people couldn't make networks deep. They just didn't work. At some point, you'd add another layer and your performance would get worse. And you'd say, okay, this doesn't make any sense. Like, you know, why is this happening? And the reason, or maybe a reason, but a big reason, is that the deeper our networks got, the larger the vanishing gradient problem became. So the vanishing gradient problem basically is just, it's this idea that, yes, as our networks get deeper, we've got to do this backpropagation from the output of our neural network all the way to the input, changing the parameters as we go. The problem is that that signal, that backpropagation signal, as it goes through a really deep network, what's happening is it's getting multiplied by weights. And one of two things is going to happen. Either that gradient is going to vanish or explode. More often than not, with feed-forward networks, it vanishes because the weights are all less than, or less than 1 and greater than 0, well, -1 usually. So they're between -1 and 1, which means that if you keep multiplying your signal by that value between -1 and 1, it's going to get smaller and smaller and smaller and eventually vanish. Now, this was compounded by the fact that the sort of dominant activation functions at the time were the tanh and sigmoid activation functions. So Linnet, for example, used tanh. And the problem there is that sort of where those two functions get saturated, remember they're sort of an S shape, and sort of as you get further and further away from 0, closer and closer to negative or positive infinity, those functions saturate. And what happens there is that we've got a very flat function, and a very flat function has got a very small gradient. So again, we have this vanishing gradient problem. So this is somewhat solved by using something really simple like a ReLU, which doesn't saturate. It's just a ramp function, so it's flat, and then sticks up at an angle. So the gradient is 0, and then a constant value. So a ReLU will never cause vanishing gradients. It has got other problems. Our weights could get stuck in a position where the ReLUs are always turned off, sort of in the 0 section where there's no gradient, and that can be a problem. That's solved by initializing our neural networks quite well. There's all sorts of schemes for that. But by and large, using ReLUs is much better than using, say, tanh or sigmoid in the middle of our neural network. So that was one thing they did different. Is that a question? Okay. Can we get the mic on? There we go.
Hey, so I'm getting a little lost
Okay.
in you explaining how AlexNet works.
Sure.
I just wanted to confirm if I'm following along.
Sure.
So does the convolutional layers and the max pooling layers happen prior to the activation layer? In the case of AlexNet, does the activation function in itself actually exist as a layer, as opposed to being applied to a node within a layer?
Sure. Okay, so that's a bit of a philosophical question, in fact. And it kind of depends on what sort of deep learning framework you use, whether the framework will view it as a layer in and of itself or as sort of part of another layer applied to each node. But it doesn't actually matter which way you think about it. You can view it either as applying a convolution layer and then applying a ReLU activation layer, or you can view it as like the convolution as part of that layer is going to apply a ReLU function. But it's actually equivalent in the end. But let me actually take a little step back. Let me go back to this picture just so we make sure that everyone's on board with AlexNet. So it's actually a very simple neural network. There's nothing too crazy about it. You can actually ignore this idea of grouped convolutions. In the end, that's just like a little implementation detail. what AlexNet is doing is we take an image, we apply a convolution. And that convolution in this case has got an 11 by 11 filter, and we have a stride of 5, which means we move that filter across 5 pixels each time. Then what we do is some pooling, and in this case, I guess it's 5 by 5 pooling, so each 5 pixels, we take the maximum of those, and we get another image, and then we apply another bit of convolution. Actually, you know. Anyway, so yeah, it's the same idea as the net, right? It's convolution layer followed by pooling layer, convolution layer, pooling layer. And yes, after each convolution, there is an activation function, which in the case of AlexNet is the ReLU, and in the case of LeNet is tanh. But yeah, there wasn't actually anything that crazy about AlexNet, which is the point I was sort of trying to make, which I guess by trying to make it, I didn't make it. Because I didn't really go over the architecture. I wanted to just, there wasn't anything in particular to talk about with this architecture. It's much the same as the net, just sort of scaled up, put on a GPU, and then they've got a few tricks to make it train better. So one of those tricks being using ReLU. So yeah, the ReLU function, pretty great stuff, but also not super complicated. The other thing they did was they used something called Dropout, and Dropout is a technique for reducing overfitting. And basically, if we apply Dropout again to some array of numbers, it can be any shape array, but over here we've got 2D because we're dealing with images. All we do is we set a hyperparameter called our dropout rate, and that controls basically how many of our values we throw away. So a sort of typical value there is 0.5, so in this case, I'm randomly throwing away 50% of the values. And I've sort of highlighted those in a pinky reddish color over here. So we've zeroed all of those out, we've thrown them away. Why do we want to do that? So the reason for throwing out our values and zeroing them out like this randomly is that we want to prevent sort of co-adaption, meaning that, if you see a 6 and a 9 next to each other, maybe that's very predictive. Maybe that in our training data set, we're classifying faces, and somehow along the way it's come into being that if there's a 6 next to a 9, that's a face. But it might be that a 6 next to a 9, meaning a face, only happens in our training data set. And we want to make sure that we're not getting stuck on sort of the nitty-gritty details of our training data set that might not apply to the real world. So what we can do when we're training is we can throw away some of the pixels, and what that might mean is, for one example, you don't see the 9, or for another example, you don't see the 6, and then another you see neither the 9 or the 6, and a fourth one you'll see a 6 and a 9. And that way it's less likely that our neural network will learn that, yes, those two specific values are incredibly predictive of our output. And this is typically applied only in the fully connected layers of our neural network, but you can also apply it to a convolutional layer. Basically, any layer in your network where there's weights, you can apply dropout, and that'll sort of prevent this co-adaption. And as I mentioned, typically we'll use like a 50% dropout rate, but that's typical for a fully connected layer or a dense layer, it's the same thing, just I often say dense, which is like a less common terminology, I guess. So just if I say dense, and all my slides say dense, but fully connected, just think it's the same thing, because it is. If you're applying dropout to a convolutional neural network, you'll usually use a much lower dropout rate, maybe 20% or 10%. And you can even apply dropout to your input image. Throw away parts of your input, and again, there you'd use a much smaller dropout rate of like 10%. There is one trick with dropout, which is that it's only something we do at training time. So we don't want it to affect how our neural network works at test time. So you'd think, okay, fine, just don't do dropout at test time. The problem with just not doing dropout at test time is that, if we look at this image now, compared to this image, the mean and variance are totally different, right? Well, in particular, the mean is totally different. We've zeroed out a lot of values, and so sort of the distribution there is different from this. And that shift in distribution as a result of using a dropout layer can actually negatively affect the layers that follow our dropout layer, because they will get used to seeing a particular distribution of data at training time, and then at test time when we say, okay, let's not use dropout, they'll see a different distribution and things can go a bit wonky. So the sort of trick there is to, yep, we throw away half our values in this case, but for the half of the values we don't throw away, just double them, right? We've thrown away half our values, so if we double all the remaining values, we should get roughly the same mean, for example. So that's the only other little detail about how dropout works, but otherwise it's a fairly straightforward technique. Okay, so yeah, I hope you'll agree with me that there's nothing particularly crazy about AlexNet. They just scaled it up and had a few tricks and tweaks to make it train well, and it did totally amazingly in ImageNet. That was in 2012. In 2014, we had VGG come along, and this was another network that performed really well on ImageNet. It actually only placed second, and spoiler alert, we're going to learn what placed first in just a moment. And again, there's nothing really crazy about VGG. If we look at the architecture over here, it's very much the same idea of convolution followed by activation, followed by pooling, followed by more convolutions, followed by more activations, etc. And then eventually we have a dense or a fully connected. We have a couple of those with activations in between them, and we get our output. So again, the structure here is much the same as AlexNet. In fact, the structure here is much more simple than AlexNet, and that's what's really interesting about this network and why I wanted to talk about it a bit, is that there's no grouped convolutions. There's no 7x7 convolutions or 5x5 convolutions. There's no variation in the amount of pooling. It's basically a very uniform structure where every convolution is 3x3. Every convolution uses the same amount of stride, amount of pooling. Sorry, not pooling. The other word I was looking for was when you add zeros around the edge. Can't remember the word. Padding, there we go. So that was also, sort of standardized. Same story with our pooling. It only used max pooling. The max pooling was always 2x2. The padding for the pooling was always consistent, things like that. But this network did very well. And in fact, there's two variations of this network. There's a 16-layer version and a 19-layer version. So I guess another big difference between, well, I guess the big difference other than the sort of standardization between VGG and AlexNet is that it's many more layers. So I'm not actually sure how many layers AlexNet has in total, but it has 5 convolutions, for example. And already we can see here there's like, okay, 4, 9. So here there's like 13 convolutions. So that, it's a much deeper network. And again, that was sort of people wisening up to how to train deep neural networks. No particular interesting tricks here, other than, I guess, maybe by standardizing on 3x3 convolutions and 2x2 convolutions, the training was easier. But interestingly, this is where things got stuck. So people were like, yes, a 19-layer deep neural network. Now we can really call this deep learning. But how much further can we go? And the answer was no further. They couldn't add any more layers. They found if they added a 20th layer, the performance started going down. If they added a 21st layer, it went even further down. If they added a 23rd layer, guess what? It kept going down. And the reason that happened was this vanishing gradients problem I told you about. They had ReLU, they had all sorts of other nice techniques, but they still found they couldn't make it any deeper. So what could we do? If we can't make it deeper, let's make it wider. And that's what Inception did. Inception was the winner in 2014, eking out first place over VGG. So, okay, what's the basic idea of Inception? As I mentioned, it's wider rather than deeper. Okay, yes, it's still 27 layers, which is more than the 19 of VGG, and I'll get to how they did that in a little bit, but that's not the main point. That's not the takeaway of this network. So how did they go wider? They used what's called an Inception Module, which is what I've drawn here. Well, I've drawn a sort of naive Inception Module here. But the idea there is, how do you choose between a 5 by 5, a 3 by 3, and a 1 by 1 convolution, or any convolution size for that matter? Or how do you choose between having a convolution layer and a pooling layer? You know, these sort of architectural decisions are quite difficult, so let's not make the decision. Yet, let's use all of them. Let's have 1 by 1, a 3 by 3, a 5 by 5, and let's do some pooling. So that's what they did. Basically, they take their input. So this diagram here is what's called an Inception Module. So what the Inception Module does is it takes an input and it outputs something like any other. So you can view it like any neural network layer, input, output. But what it does with that input to get to the output is quite interesting. It feeds that input into a 1 by 1 convolution, a 3 by 3 convolution, a 5 by 5 convolution, and a pooling layer, and then concatenates all those results together. Specifically, it concatenates them together in the channel dimension. So that's sort of like, you know, in our black and white image, we had 1 channel. In our color image, we have 3 channels. You know, if we have a convolution layer with 5 filters, the sort of output image from that convolution layer will have 5 channels. So they concatenated all of these things together in 1 channel. So you can kind of picture this as 1 convolution layer which has got a mixture of filters. It's got some 1 by 1 filters, some 3 by 3 filters, and some 5 by 5 filters, as well as like the random pooling thrown in. So yeah, the sort of trend prior to this with sort of VGG was that we don't need all these different size convolutions. Basically, everyone was using 3 by 3 convolutions. And in fact, that's still pretty good advice. If you don't know what size convolution to use in your network, 3 by 3 is not a bad choice. But with this one, you know, now all these different sizes are making their comeback. So we're starting to see 5 by 5s and weird things like 1 by 1s. Yeah, 1 by 1 convolutions. Is anyone sort of uncomfortable with that? Okay, that's good. I was also uncomfortable with it because it doesn't really make sense, right? We've got an image and we're applying our convolution to a patch of pixels in that image, but now we're only looking at 1 pixel, so like what is that even doing? But what you're sort of forgetting, or the sort of detail that is being ignored with that line of thinking, is that it's 1 by 1 by some depth, right? We're applying it to an image with depth, some number of channels. So when you're actually applying a 1 by 1 convolution, you're looking at a particular pixel, but you're looking at all the channels for that pixel. And so what we're doing is we're sort of learning a relationship between those sort of like the pixels that go into our image. The depth of our image is now what's important. And you can actually do a whole bunch of really cool tricks with 1 by 1 convolutions, which I'll get into a little bit later. But so yeah, don't worry about 1 by 1 convolutions. Just remember, our image isn't actually just a 2-dimensional plane, it's some volume with depth. And the 1 by 1 convolution does something in that depth direction. Oh yeah, if you are interested in 1 by 1 convolutions, they were introduced in 2013 in a paper called Network in Network, which was a really cool paper, so you could check that out. Okay, so the image I showed you on the previous slide was a sort of simplified view of what the Inception module does. And this is sort of a more accurate picture of it. And you'll see what's been added is a whole bunch of 1 by 1 convolutions again. So why would we do that? Well, the reason we do it is to reduce the number of parameters in our network. So what's happening is, let's say our input to the Inception architecture has got 10 channels, all right? That means that our 3 by 3 convolution would have to act on those 10 channels. However, let's pretend for a moment that the input was 5 channels all of a sudden. Then our 3 by 3 convolution, they would only have to act on those 5 channels, and it would be twice as efficient. It would take twice as quick to run and have 2 times fewer parameters. So that sounds great, right? Why don't we just use less filters in our previous layer? The problem with using less filters in the previous layer is that, well, then we're learning less interesting things, you know? If we only use 5 filters, that means we can only learn about, say, a nose, an eyebrow, an ear, a mouth, and, you know, eyelashes or something. But if we add another 5 filters, we can learn about maybe cheeks and chins and all sorts of other things. So having more of these filters in our convolutional layer just increases our sort of model's expressiveness, the things it can see and understand, the sort of features in our image it can pick out. So we don't really want to throw things away. With things like graph convolutions and whatnot. The sort of when to not use a convolution is if you can make a grid out of it and then swap the order of the rows or columns without affecting the results. If you can do that, then the convolution is not the right thing for you. But if swapping the order of columns and rows messes things up, then you know, okay, let's use a convolution. That's all. Thanks so much. Are there any last questions?
Okay, thank you for the presentation.